In this episode, we are comparing the deflection of two types of beams. In one case, we can see here on the top a simply supported beam with a point load in the center, and in the bottom we can see a 3-hinge beam with the same load also in the center, with the 2 hinges at both extremes being fixed. So that means they can't move either up or down or sideways. And the question is, which of the two beams has a larger deflection in the center? Well, let's start by looking at the 3-hinge beam, or a catenary, elastic catenary. If we look here on the top left, we see the deformed shape with the vertical deflection delta in the center. We're going to denote each half length as L. And in that case, then the stretched length becomes square root of L square plus delta square. That's this expression right here. So the stretch length minus the original length gives you the elongation of the member. So that's square root of L square plus delta square minus L. Multiply that times AE over L and you get the tensile force that is developed in that member as the catenary deforms and elongates. So now looking here at the top right, we see the free body diagram of the center hinge, and we have the two tensile forces T acting at an angle theta. We have the vertical force P going down, and by simple equilibrium we obtain this expression here for T. T equals P divided by 2 sine of theta, but sine of theta is opposite over hypotenuse, which is delta divided by square root of L square plus delta square. That expression we substitute back in our deformation force relation and solve for P, and we obtain the expression here at the bottom that relates the vertical deflection under the center hinge to the vertical force P. To simplify the expression a little bit and make it more workable, we are going to express everything in terms of the slope. So delta over L equals alpha. And if we do that, the expression simplifies to this expression down here after a little bit of algebra. And that expression again relates the vertical force P to the slope of the deflected shape. And here it is again. This is our deformation delta. The slope alpha equals to delta over L, and the expression that we just showed that relates the force to the deformed slope. Now, going back to our simply supported beam, we know from basic mechanics of materials and structures that the deformation in the center of a simply supported beam with a point load is equal to P times the length cubed divided by 48 EI. In this case, the length is 2L, remember, because we are using that L as half the length, and so we have to cube 2L. And so that results in this nice expression here after we divide the deflection by L, and we get that the variable alpha, which is delta over L, equals PL square over 6EI. Now we can simply compare the force in the simply supported beam versus the force on the elastic catenary. If we look at those expressions, what we see is that this kind of behavior comes out. So basically the beam has a linear behavior, assuming all of the basic assumptions of small deflections, elastic, linear materials. But the catenary has this nonlinear behavior. But at some point they will meet, and that point we're going to call alpha C. So there is a critical alpha value for which the force in the catenary and the force in the beam are the same. Below that critical value, the deflection in the beam for a given level of load is smaller than the catenary. Beyond that value, the deflection in the catenary is smaller than the one in the beam. So we're now going to go and find that value, equating these two expressions here. The alpha in the numerator cancels out, the elastic modulus cancels out, which is interesting because it basically means that if the two beams are made out of the same material, the answer doesn't change. And then we can send 2a over to the left side, and we get this constant, which we're going to call beta, which is 3I over AL squared. And the critical value of alpha, the value for which both beams have the same deflection given the same load, can be found from the solution of this expression right here, which we obtain by simply solving for alpha C, and we get this expression here shown in the yellow box as a function of beta. Remember, beta depends on the moment of inertia, the area, and the length of the beam. So again, this alpha C is delta C divided by L, where delta C is the vertical deflection for which the beam and the catenary have the same vertical reaction. If we want to look at that in the case of a specific type of cross-section, so let's say we're looking at a rectangular cross-section, this value of beta comes out to be 1 over 2 lambda squared, where lambda is the length divided by the depth of the section. So there you have it. The answer is that for small deflections, the beam is stiffer, but as the deflection grows, the catenary becomes more stiff.